This video is about circuits that involve resistors, inductors, and capacitors. In particular, we're going to be looking at the impedance of the series and the parallel connections of these. The series connection of a resistor, an inductor, and a capacitor is going to have an impedance which is just the sum of the individual impedances. So that's R plus j omega L plus 1 over j omega C. And that's the impedance. Now, these two parts, the inductance and the capacitance, both give an imaginary part to the impedance, and the resistance gives a real part. So it's useful to group the imaginary parts together to write the impedance as R plus, getting this over a common denominator, we're going to get 1 minus omega squared LC over j omega C. And this shows us a few things. One is we can look at what happens at interesting frequencies. For instance, as omega goes to 0, the omega squared term basically disappears. 1 over j omega C gets very large in the imaginary sense, so this goes to 1 over j omega C. It behaves like a capacitor. As omega goes to infinity, the omega squared term now gets very large, even after dividing by the omega. So we end up with something that goes to j omega L. So at DC, or very low frequencies, it behaves like a capacitor. At very high frequencies, it behaves like an inductor. And there's a place, of course, where it makes a transition between these two, and that is where omega is the square root of 1 over LC. So that you've got 1 minus omega squared LC is 0. The imaginary part goes away, and there we have Z equals R. So we've got something that behaves like a capacitor at low frequencies, behaves like a resistor at the resonant frequency, and behaves like an inductor at high frequencies. Let's go through the same analysis now for parallel connection. Now we have the resistor, the inductor, and the capacitor all in parallel. For these, we're going to have Z is 1 over R plus 1 over j omega L plus j omega C. This is just parallel impedances are 1 over the sum of the inverses of the impedances. And again, this is a little messy, and we can simplify it if we multiply top and bottom by R times j omega L. So we have R times j omega L over j omega L plus R plus j omega RL, sorry, that's minus omega squared RLC. The j omega part gets squared. Okay, this can be written perhaps a little more simply if we write j omega L over j omega L plus R times, so there's an R on top, R times 1 minus omega squared LC. Because this shows us again that we have a resonance where this part, which is now the imaginary part because the imaginary over real, the imaginary part will again go to 0 when omega squared is 1 over LC. Okay, so we've got taking a look at what happens as omega goes to 0. The omega squared term becomes negligible. The j omega L term here doesn't really matter, and so we end up with j omega L r over r. So z goes to j omega L. And as omega goes to infinity, the omega squared term is now the important one, and we have the r's again cancel, and we get j omega L over minus omega squared LC, which is just 1 over j omega c. And when omega is equal to 1 over square root LC, this part disappears. We have j omega L times r over j omega L. It's just r. So now we've got an inductor at low frequencies. Remember previously we had a capacitor at low frequencies. Now we've got a capacitor at high frequencies. Previously we had an inductor at high frequencies. But at the resonance we again just have r. Okay, it's probably worthwhile to plot these things out using GNU plot. So let's take a look at what that gives us. Here's a script loading definitions to get all the definitions of ZL and ZR and parallel connections. And I'm going to plot both the LC circuit without the resistor, which we did in a previous video, and adding in the resistor. So for series, it's just plus R. And for parallel, I use the ZPAR3, which takes 3 things in parallel. Basically, this formula is built into ZPAR3, where you have Z1, Z2, Z3 as the 3 parts here. 1 over Z1, 1 over Z2, 1 over Z3. So I'm going to plot both the series and the parallel versions all on the same plot. There's the GNU plot terminal and the resulting plot. So what we've got here, the blue and the green lines are without the resistor. We have at the resonance we have it going to 0 and to infinity, depending whether we're series where it goes to 0 or parallel where it goes to infinity. But what happens when we add that resistor either in series or in parallel is that we basically clip off that big spike, the resonance spike, and at resonance we just have the resistance R. And you can see that you can use this to control what happens at the resonance almost independently of what happens elsewhere. Outside the region around the resonance, the RLC circuit behaves essentially the same as the LC circuit. And how far away from the resonance it starts behaving like just the LC circuit depends to some extent on what the resistance is, because it's going to basically trim off everything going beyond a certain point. And you can see for the values I picked here, where the resistance is 330, only a little bit of the parallel connection is changed, but a lot of the series connection is changed because we're looking at a fairly large resistance here relative to what the LC circuit is providing. Okay, and I think that's enough of a summary of RLC circuits.